show you a few more examples on how to find absolute extrema of functions of two variables. I've decided to do this basically one example at a time because otherwise the videos are becoming a little bit too long. So here's the first example. So actually first, before we do that example, let's do a quick summary of how to find absolute extrema. We've already gone over this in the pre-class materials, and you might find it helpful as well to look at the summary sheet for week 10, where this is also summarized. So what we're interested in now is to find absolute extrema rather than local extrema. And absolute extrema makes sense when we're talking about a closed set in the domain in the xy plane, basically. And this is very analogous to finding an absolute extremum of a function of one variable on a closed interval. And so if you remember from the first calculus class, such absolute extremum can occur either at the interior of a closed interval or at one of the endpoints. And so it's the same thing over here. We could have a critical point on the interior of the domain D, or I should really refer to it as the set D. And when you've got a critical point in the set D, that could be a local max or a local min, but we also need to take a look at the boundary, because it may be that you have a local extremum on the boundary. So I actually want to make it very clear that this first point here, this first step, is not sufficient. So it is really important to note that it is possible that there are no critical points. So that there are no critical points in D, or it may be that there is a local min, for example, on the interior, and the local max. Oh, sorry, I shouldn't say that. There's a local min on the interior, but you're interested in an absolute max. But you're interested in the absolute max, which may then occur on the boundary. All right, so let's go to that first example then. So I've already done a little bit of work, again, to cut down the length of the video. So here we're interested in finding the absolute max and min values of the function f of xy is equal to 1 plus 4x minus 5y. And we're interested in doing that on this triangular region in the xy plane, which has the vertices 0, 0, right at the origin, the point 2, 0, which is on the x-axis, and the point 0, 3, which is on the y-axis. So the max and min values could occur on the interior, which is that yellow region, or they could occur on any of the three components of the boundary, and I have labeled them L1, L2, and L3. So L1, we need to put some equations to that. On L1, for sure, y is equal to 0. So y is equal to 0. And we're restricted the values of x. They have to be between 0 and 2. Similarly, on L2, we know for sure that x is equal to 0. And we have a restriction on y, namely that y lies between 0 and 3. Now, L3 is a little bit more complicated, but I know that you can all do this, so I'm going to leave that as an exercise. But we basically need to find the equation of the straight line, and I'm going to say that is equal to y is equal to 3 minus 3 halves x, with the restriction that x lies between 0 and 2. And so for you as an exercise to find the equation of this line, you might want to realize or recall, no, not recall, you might want to observe that we have a line with slope minus 3/2, so it's rise over run, but we definitely have a negative slope, so it's minus 3 over 2, and a y-intercept at 3. All right, so we have just characterized the boundary, and now we have set up the problem so that we can do steps number 1 and 2 of that algorithm over here, or these steps over here, right? So we're going to start with finding the values of f at all critical points, and then we'll go on and consider all components of the boundary. All right, so example 1, we are now on this page, right? So the first step is to look for critical points inside the triangular region. And are there any local extrema present on the inside? So to find the critical points, we have to set the partial derivative with respect to x and the partial derivative with respect to y equal to 0. Well, let's find the partial derivatives. F sub x is the derivative of 4x, so that's just 4 actually, because the derivative of 1 and minus 5y are both equal to 0 as far as x is concerned. And f sub y, similarly, is just minus 5. So actually, this is very interesting, hey? Because we cannot set those partial derivatives equal to 0. That says that this whole function does not have any critical points. So, so these cannot be 0. So these cannot be set to 0. And therefore, this function has no critical points at all, let alone inside the triangular region. So right away we know that the absolute max and mins have to occur on the boundary. Okay, so that is then step number 2, is we look for extreme values of f on the boundary of the triangle, and we need to consider all 3 parts of the boundary separately. So let's start with L1. L1 had, we found the equations for that. We characterized L1 mathematically. We said on L1, it is true that y is equal to 0, and we have this restriction that x has to be between 0 and 2. So what does the function f at xy become under these restrictions? Well, certainly y is equal to 0, so we're looking at f at x0, and so we set y equal to 0, and then we end up with just simply 1 plus 4x. And now we consider a restriction that x lies between 0 and 2. And of course, the larger x is, the larger the f value is. So right away, we can say that the maximum is obtained when x is equal to 2. So at the point xy is equal to 2, 0. That's one of the vertices. And we can calculate the the z value right away. So the maximum value on L1 is f at 2, 0, which is 1 plus 4 times 2, which is equal to 9. The minimum value is obtained when x is equal to 0. So at the point xy is equal to 0, 0, and we can say that the minimum value on L1 is f at 0, 0, it's at the other vertex, and that is equal to 1 plus 4 times 0, which is equal to 1. Okay, so now we need to do the same work for L2 and L3. I'm going to go through that a little bit faster. I've done already a little bit of pre-work on this. So on L2, x is equal to 0, and we're working with the restriction that y is between 0 and 3. So what is f at xy under this restriction? Well, x is equal to 0, so we're looking at f at 0, y. And so when we set x equal to 0, we end up with 1 minus 5y. Okay, and again, now we oppose the restriction that y lies between 0 and 3. So the maximum is going to be obtained when y is equal to 0. So when y is equal to 0, so at the point xy is equal to 0, 0. And so the maximum value on L2 is f at 0, 0, which we already calculated actually. It's 1, but we can calculate it a different way now. It's 1 minus 5 times 0, according to the equation that we just came up with, 1 minus 5y, and so that's equal to 1. Similarly, the minimum is obtained when y is equal to 3. So at the point xy is equal to 0, 3, and the minimum value is then f at 0, 3, which is equal to 1 minus 5 times 3, which is minus 14. All right, now the last one, that one looks to be the most complicated, but it's actually just as straightforward. As long as you, I always like to say, as long as you follow your nose, you just go through the steps and you'll figure that out. So f at xy, under the restriction that y is equal to 3 minus 3 half x, is equal to 1 plus 4x minus 5 times y, but y is 3 minus 3 over 2x. Okay, now you can certainly do the algebra and simplify this, and what you'll get is that this is equal to minus 14 plus 23 over 2x. And now we impose the restriction that x lies between 0 and 2. Okay, now so the maximum is going to be obtained when x has the largest value, so when x is equal to 2. So at the point xy is equal to 2, 0, the maximum value on L3 then is f at 2, 0, which is equal to 9. And the minimum is obtained when x is equal to 0, so at the point xy is equal to 0, 3. And the minimum value on L3 is f at 0, 3, which with a little bit of algebra you find is equal to minus 14. All right, so we have done a lot of work, and the next step is then for us to summarize all of that work. So I'm putting everything together now on this slide, and I've already pre-written this slide because it just saves a little bit of time. So don't forget, on the interior we had no conclusions or no critical points. So we cannot find a local min or a local max on the interior. On L1 we found a max and a min, and if you go back through the notes you'll see that we found a minimum value of 1 at the vertex 0, 0. We found a maximum value. Sorry, I've turned these ones around, haven't I? This is equal to, this is the max. And these are the mins. All right, and so same thing on L2 and on L3. And so then if we look overall in the entire table here, the absolute maximum is 9 at the point 2, 0, and the absolute minimum is the minus 14 at the vertex 0, 3. Okay, and so I have summarized that at the bottom of the page. The max is 9 and the min is minus 14. So last but not least, we can take a look visually how this works. So it turns out that the function 1 plus 4x minus 5y is a plane, and it's visualized here on the left. In 3D, what I've done is actually on the XY plane, I have drawn out the triangular region, And then you can see how the plane is sitting on top of that triangular region, and the minimum is found at the back there, at the point 0, 3, minus 14, and the maximum is right here at the front, so at the point 2, 0, 9. If you're looking on the right-hand side, there you have the contour plot. The darkest regions here are corresponding with low values of Z or of F, and the lighter values are associated with the higher values. And so the absolute min of minus 14 is obtained at the vertex 0, 3, and the maximum of 9 is obtained at the vertex 2, 0. All right, so that concludes this particular video, and I'll catch up with you at the next video. Bye-bye.